Yeah, and before, can you also send me the YouTube link to the YouTube? I'll have to send, yeah, okay, mail. I have the older one. Is there a new one? Uh, yeah, no, I'm looking at it. Link is there. Oh, okay. Yeah, it's there. I got it. Yeah, I got it. Yeah, you can go live. Okay. Welcome to this second live session related to the nuclear and particle physics course. So, thank you all for joining. Okay, so we have actually advanced somewhat into the understanding of elementary particles, I guess, in the course. So if you have gone through the materials, then you would now know what are the elementary particles. By elementary, we mean particles which cannot be thought about as constituents of some other further smaller particles like electron. Electron is, for all practical purposes, a point-like particle without any dimension that we can, or an size that we can attach to it. And it's believed so far there is no indication that electron is made of any smaller constituents. Unlike, for example, proton is made of quarks. Similarly, quarks themselves are elementary particles. So we will actually today discuss one particular uh, issue, not really a big issue we solve because we have already found solution to it. But this was one of the hurdles in the early days of the development, and for some time towards, I mean, in a sense, it was now established only very recently, about 10 years before, that this mechanism that we are going to talk about is indeed a right way of going ahead with understanding the elementary particles. Now, electron we know has mass, and similarly we have protons which has mass, atoms have mass, and all other complex system also have mass. Mass is a property which is assigned to a particular system. Complex systems like us or any objects, chair, table, tree, or just any bulk of some particular matter like iron or anything. So that we actually assign that, and then that's a property that we understand in different ways at different levels. In the classical regime, in the day-to-day understanding of what the properties of or physical phenomena that we have around us, we consider it as a property that is required to have gravitational interaction. Okay? Weight is because of basically the gravitational attraction. Weight of any body on Earth is due to its mass, and because of its mass, it is attracted to the Earth, and this force of attraction causes the force which we generally call weight. But in the elementary particle description, this is not a very good idea. So there are other ways to understand what is called mass. In a very crude sense, mass could be considered as the energy of the particle when it is not moving in its rest frame. So what is the energy of the particle in its rest frame, if we can ask? Then that is the mass, that is the energy due to its mass, its own property. It's not because it is moving, but it is an inherent property. Moving particle will have kinetic energy in addition to its mass. Okay, or if it is put in another interacting potential, it will have a different energy. Either it will give away energy or it will take energy through interactions. How do we understand the energy at rest, a particle which is at rest, not interacting with something? That is what we can call as mass. For elementary particles like electron, we have such mass. So if it is a complex particle like a proton or neutron, then we can think about it as, again, energy can be arising through interactions of its constituent particles. Like even in the case of atoms, we can think about interaction between constituents, or in nucleus case. So there are a lot of energy that you can actually think about being contained in these such kind of balls of these particles which have constituents. Okay, so that's one way of thinking about it for these constituent particles. Yes, that is okay. And same thing with the complex systems like us. We can think about a lot of many different complex molecules in us, and there are a lot of interactions that happens, and this interaction energy, sum of all these will actually give us some kind of a energy when we are not doing something at rest, and that's our rest energy, which is the mass of us. But for an electron, how do we understand it? It has to come from a different view, or it has to be understood in a different way. That's what we are going to discuss shortly today. Okay. Okay. So just to brief, what we may have already considered in hello Arnav. Yeah, somewhere the connection was lost. Now it is okay. You can continue, right? Okay, fine. Yeah. So Sorry for the interruption. There's a technical glitch. Uh, as we were talking about the interaction of elementary particles. So interaction of elementary particles, like for example, if you consider the Rutherford interaction, where there is a nucleus and there is an alpha particle which is projected towards it. They have some interaction and therefore the alpha particle scatters off this one. And this is an electromagnetic interaction, we know that. And this electromagnetic interaction in the particle physics fundamental, at the fundamental level, we understand it as interaction through the exchange of photons. The electromagnetic field can be thought about as collection of photons, particles, quantum particles, which are called photons. Similar to these photons, we have weak interaction gauge bosons, W and Z, and for strong interaction, we have what's called gluons. So this is the way that we understand different interactions, like the electromagnetic interaction, weak and nuclear interaction, weak and strong nuclear interactions, through the exchange of such photon-like particles. Okay, all of these also have mass. We know we have actually seen this. The photon, not all of this. Photon does not have any mass, and gluon, which is causes the strong interaction, that also does not have any mass. But weak interaction gauge bosons have large mass. Its mass is quite large. You can compare here that with the electron mass. Mass of the electron is 0.5 MeV, whereas W and gauge bosons, Z boson, has close to 100,000 MeV. Okay, this is called 100 GeV. Okay, that is the kind of mass that it has. So it is about 100,000 or 200,000 heavier than electron. Okay. Now, that's one side of the story that it also has. Now, also the fermions, like electron itself, has mass, right? And all other quarks also have some mass. I have listed here masses of all the non-particles. Okay, all the elementary particles that we know now. Top quark is the heaviest of all the elementary particles. It is quite large, 173,000 MeV or 173 GeV. That is its mass. Okay, so such all these particles, the top quark included, do not have any elementary more elementary constituents. So it cannot be understood, and mass of this cannot be understood through masses and interaction of the constituent particles. How do we understand that? So there was a long way. There was a lot of investigation in different directions, debate of what could be the possible things, etc. And one of the ways that was cute and nice, and which worked out all right with all other aspects of the fundamental interaction, is known as the Higgs mechanism. So, and now very recently meaning in 2012, there is a new particle called Higgs boson, which is a scalar particle, which was discovered, and that actually confirms that this could be thought about what we thought about as the mechanism to generate the elementary particle mass is correct. That is where we stand now. So let me briefly tell you what is this Higgs mechanism. First, before going into any technical details in terms of equations, etc., I will give you a heuristic argument about how this can be perceived. How do we actually see it in terms of something that we already know as a property of massive objects. Okay, so it's like that. If we actually let us think about a situation where we are actually walking on a plane surface, okay, and we can actually freely walk there, right, without any hindrance. Forget about the air resistance. Barring that, we can walk. So at the speeds at which we are walking, it's kind of air resistance is completely negligible, and therefore we can think about it as a free can walk. Okay, there is no resistance that is offered to this walk that we have. Okay? Now let us do the same thing in a puddle of water or in a pool, which is kind of filled with water a little bit up to say let us say 1 foot water. Then when we walk in that water, we have to we will have some resistance from the water that we have. Okay, and that will interfere with our walking. So it will kind of reduce our speed. There will be a kind of an inertia because of this interaction of this water with our feet. And it depends on a similar thing that you can imagine as say dragging some object. Okay, on a completely say the frictionless surface, if you just drag it, one of the things that you can think about in air or vacuum, that will just flow without any hindrance. Whereas if you do the same thing, although the surface itself is without anything, there will be if the medium is, if you are dragging it through water, then it will actually be deterred because of the drag. Now that's basically in because of the interaction that the surface at the surface this water the layer offers to this object that you are dragging. Okay, so this can be, this is a hindrance to this thing. So we can actually think about it in such a way that it is inertia that comes in or heaviness is considered through some kind of an interaction with something which fills this medium in which we are moving. But electron has, it is a very heuristic picture. So, I mean, the more technical details will not have any such analogies that is required. But this is the kind of an thing to understand, or if you want to make a mental picture. But the electron has mass even if it is moving in free space. There is, what is the medium we are talking about? Therefore, what is proposed is that what we consider as vacuum now, that is empty space, completely empty space, is basically filled with something which we don't see, perceive, or detect otherwise. We cannot detect it in whichever way, neither gravitationally nor with electromagnetic interactions or strong or weak interactions. This is something is the property of that field. Let us call it a field which is filling it. So we call it the the field which is the Higgs field. Okay, so this is a Higgs field. The Higgs is a name. The name is associated with the scientist who proposed this, Peter Higgs. And there are also other people who, along with him and Abel, in fact, at the same time, almost the same time, independently proposed similar these things. All of it is the same kind of an idea. So, therefore, the Nobel Prize, in fact, was shared between these people. But the name is stuck with Peter Higgs. In fact, the application as such that we consider in particle physics is owing to Peter Higgs quite a lot. Anyway, so this is called the Higgs field. So this Higgs field is something which fills all space, including the empty space. So the vacuum, as we consider as vacuum, is not completely devoid of everything, but it is filled with some kind of presence of Higgs field. Now we can say that the electron, when it is moving through this Higgs field, there could be some kind of an interaction between these, and this interaction between the the electron and the Higgs field is going to give some kind of a property which we can actually consider as the mass of this one. Okay, it can be technically clearly understood. That is exactly the Higgs mechanism, the details of the Higgs mechanism. how do we identify it as mass, etc. Okay, we are going to just very briefly talk about that in the next few slides. Not only the electron, but all other elementary particles like U quark, D quark, top quark, all other things can be thought about as having this kind of interaction with this Higgs field, and then generated, or mass is basically the manifestation of this interaction, because we don't see the Higgs field otherwise, we see only electron, and this interaction therefore has to be attributed to that electron or that particular particle. Not only these particles, but all these W boson and gauge boson, the Z gauge boson that we talked about, also gets the mass through this interaction, same interaction, and the interactions differ. Therefore, the mass also differs. So the difference in the masses can be again attributed to the difference in the interaction strength in a way. Okay. That's how we understand this. So the elementary particles now include what's called the Higgs boson as well. So the remnant of this is that because of that Higgs field, the way that its mechanism is introduced and is worked out, there will be an elementary particle which has to be there along with all other elementary particles. And indeed, we have found this particle in the elementary collisions of the proton and proton at the Large Hadron Collider. Okay, so that is the great success of this standard model and the Higgs mechanism. One of the great successes, and which was the latest one, so to say. Okay, 10 years before. So, having said that, let me tell you a little bit about what the Higgs mechanism is, some technical details. Okay, I mean, some of you may not be very comfortable with this, the language that I am talking here, but you can patiently go through it slowly at your leisure later. But essential things I will try to explain here. Okay. In the non-relativistic case, you all are familiar with quantum mechanics. Schrodinger equation is the one that we consider and that you are all familiar with. So if you have a system which has a wave, which is represented by a wave function psi, the Schrodinger equation, or a particle that you are considering, which is a free particle without any potential, then it is minus h cross square over 2m del square psi is equal to IH cross time derivative of psi, partial derivative. And that's what we have here. And there is an exact analogy in the relativistic case, which is basically now the Dirac equation, and that is written in this particular fashion with what's called the gamma matrix, gamma mu dou mu psi minus m psi. So this m that is coming here is basically the mass, similar to minus h cross square del square over 2m is basically the kinetic energy operator, or the operator corresponding to the kinetic energy of the particle, which is moving with some momentum. Okay, so that m is the mass, therefore in non-relativistic case, and in Dirac equation also in the relativistic case, when we have this equation here like this, then this m corresponds to the mass of the corresponding particle, whether it is electron or a quark. It would be the mass of the corresponding particle there. Okay, so this other things are details. You can check that out sometime. And now coming to the interactions of elementary particles. Interactions of the elementary particles with, say, electromagnetic field, a charged particle like electron with electromagnetic field, is understood through by kind of in a way changing the free particle thing, the momentum, by changing the momentum to from p to p minus qa square. This is, and in the Jackson electrodynamics you can see reference to this and read that part. So basically it is the Hamiltonian can be written in a nice way in this fashion. So basically it is changing the momentum to adding the q times the vector potential to momentum, free momentum, and vector potential v sorry, the scalar potential V and Q to be added along with this as the electrostatic part of the energy. So this is in classical electrodynamics, and in the quantum electrodynamics, we have a similar thing which we do. So let us we consider the free electron, and the free electron, which we said that you can look at the right hand side, top right hand side corner, where we have written the Dirac equation, and that Dirac equation is the corresponding Lagrangian that we have considered is this, the way that it is written here in the first line. So LE, that is psi bar I gamma mu dou mu psi minus m psi bar psi. Psi bar is the conjugate field, and this is basically the free electron with the mass m. There's a kinetic energy and the mass energy considered due to the mass, let us say. So now, whatever is this coefficient m here in this particular fashion of writing, that's what we will identify as mass, because that is the same coefficient that comes in the right place in the Dirac equation. And Dirac equation, we know which one is mass, because that essentially is coming from the relativistic energy momentum relation, where we need to specify what the mass of the particle, and m is the mass of the particle. So that way we can actually see that whatever is the coefficient of the psi bar psi term in the Lagrangian is basically what we call the mass of that particle, electron, or any fermionic particle. Photon field, or the electromagnetic field, also has obeys what's called the Maxwell's equation, and that Lagrangian corresponding to that can be written in terms of what's called the field tensor. A nu this here is basically the potential scalar zeroth component of this, when mu equal to 0, is the scalar potential, and 1, 2, 3 component is basically the vector potential corresponding to the electromagnetic field. Or you can actually think about F mu nu, if when you write it in terms of a matrix as components of, or the components of this F mu nu are basically the components of the electric and magnetic field that we have, corresponding electric field and magnetic field. Whichever way you want to perceive this one, the Lagrangian can be written in terms of this field tensor. What we call it field tensor. Don't worry about what the tensor part here is, but this object. You can take F mu nu and contract it with the F mu nu, the contravariant thing, and that will give you the electromagnetic field, Lagrangian. So that's separately considering. Now, when we actually consider the interactions, we consider the, first of all, we will add these two Lagrangian, and also the momentum, as we said, like in the case of classical electromagnetic interaction of charge particle, we'll have to consider the momentum now modified with an added term. So here in quantum theory, the momentum operator is the space dou mu, which is the derivative with respect to space-time coordinates, and that's modified. That has an added term. We have added a IE A mu. This I comes because the momentum operator is I dou mu, so therefore we have a minus I in that added term compared to what we have earlier, right? Earlier we had P plus Q A mu, and then here we have dou mu minus I E A mu. Okay, so it's all consistent. We can do that thing. Now the point is that what is the I mean, can we actually have this kind of a mass term here? First of all, this is exactly the way that we understand other interactions as well. Okay, so first of all, we cannot add. We don't have a term for the mass of the photon. Firstly, because the photon does not have mass. Okay, but then we notice also that there is, if you take this Lagrangian, LEEM that I have written as, which is basically the electron with electromagnetic interaction. It has some property where if I change psi to by a phase, e power I q theta and psi, okay, which is a phase essentially, and a mu along with that, okay, if I change this psi to I q this one, then and make the space dependent on the space-time coordinate, then the free electron Lagrangian is not invariant under this one. Okay, whereas if we consider the electromagnetic interaction, F mu nu, I mean electromagnetic field, F mu nu, that is invariant under change of the potential. The potential is somewhat arbitrary, and then if you change that potential, the A mu going to A mu plus 1 over E dou mu theta, then pure electromagnetic interaction or Lagrangian is invariant under that. But the moment we actually introduce the interaction between the electron and the electromagnetic field, we have this term which is psi bar I gamma mu minus I E A mu psi, and that has only one A, and then that term is not going to be invariant under this gauge transformation A mu going to A mu plus rho mu theta by E. So the gauge freedom, let us call it the gauge freedom. The gauge freedom that the pure electromagnetic field had, or the arbitrariness in the potential that we had there, is not entirely there the moment we actually introduce the electromagnetic interaction of the electrons. But then there is a way to actually regain this gauge symmetry, gauge the invariance under the gauge transformation. We can simultaneously change this sign to with a phase e power I q theta, which also depends on this one, the same theta that we consider. Okay, it's a field, it's a function of x, and that's going to actually change the other term as well, psi bar I gamma mu derivative of psi. So the derivative will add one more term there. You will have to work this out, and if anybody has any interested in that, and then try to work it out, and then any confusion in that, I'll be very happy to actually attend to that, discuss through email or otherwise. Okay, but unfortunately we don't have time to do all the details here. Then our job, the main thing that I wanted to tell here is what is the Higgs mechanism, but this minimal thing is required for that. So the bottom line is that if I make this change force on psi and A simultaneously the way that it is written here, then the Lagrangian, including the interaction between the electron and electromagnetic field A mu, is invariant under such a transformation. But this does not allow, or if we have a mass term, m square nu. I did not say how this term comes or can be identified as the mass term. That comes exactly like the Dirac equation, the way that we introduced and then identified the mass term in the Dirac equation for the electron. In a similar way, for vector particle like photon, we can actually look at what is the, if it has a mass, then what would be the term in the Lagrangian, we can understand as m square mu. Okay. Now this is not gauge invariant. So this will again break the gauge invariant. This is one of the main problems now. So we will come back to this electron mass of the electron, but considering the photon mass, we cannot add a mass to the photon. That would be all right because we don't want the photon to have mass. But the problem is, it is exactly the same kind of mechanism where the quantum electrodynamics is extended to the weak, to understand the weak interactions. I'm sorry. When we do that, it is the weak gauge bosons, that A would be actually representing the weak gauge bosons. So the actual theory standard model is slightly more complex. Here I am taking a toy kind of a situation where there is only one field which is added, A mu again, and I want to give this mass. So basically we want to give mass to this particle, okay, this gauge boson A mu, and we don't want to spoil the good things um, about the gauge symmetry. So the trick that is played here is to actually consider a kind of situation where the Lagrangian is invariant under the gauge symmetry. So that makes a lot of things easy in the way that we want to uh, understand the interactions and understand the elementary particle dynamics. Especially there are issues with quantum um, interactions between these particles at the quantum level. Uh, that could actually make all these things very complex, and then uh, non-computable. It cannot be computed in. There are basically hurdles that will come in the computations of physical quantities if the gauge symmetry is not there. Or the other way of saying is that if the gauge symmetry is there for the Lagrangian, then all the problems like any of the quantum corrections or quantum interactions that we have all behave very well, and then we can actually control everything. We can compute physical quantities like scattering cross sections and various other things without any hurdles. Whereas if the gauge symmetry is not there, that kind of a thing is not guaranteed, and then in fact it is not possible in many cases. So now, therefore, the Lagrangian, we still want the gauge symmetry, and the gauge symmetry of the Lagrangian is guaranteed in this. What we do is to actually consider another field, a potential, or the scalar field, the self interactions of the scalar field, and its kinetic energy term that we have. Okay, so this is basically okay. Without going into the details of that, although some of the details are here, that what happens is something which I will tell you. So, in the particle physical system, one is that dynamics dictated by the rules or the model that we have, like that's dictated by the Lagrangian or the Hamiltonian of the system. Second is what is the wave function or the state of that system itself. So the state of the system, including the vacuum state, okay, and subsequently other system with many particles, which is obtained from that vacuum of the system. This also plays a role in the, I mean, one part of the system itself. So the system, physical system, consists of particles which correspond to these different quantum states, including the vacuum state, and the rules of the game dictated by the Hamiltonian or the Lagrangian. So the rules of the game or the equations of motion, which is encoded in the Lagrangian, is essentially given. But okay, so we see that the vacuum state is not devoid of everything, but it has the presence of this Higgs field. The way we have introduced the Higgs field in this Lagrangian, okay, we will have the presence of the Higgs field at the minimum energy configuration, which we call the vacuum. So the minimum energy configuration in this setup is not devoid of all fields, but has some presence of the scalar field. And this presence of the scalar field, in a way, generates a mass term for the physical state that we are considering. So whenever we talk about the physical states, then we can actually have a mass term for that. So this can be actually manifestly written in the scalar in the Lagrangian. When we actually explicitly write this in the basis, in a way, in the basis of that vacuum state of the physical system that we are considering, then we will see that there is a master which is there. Okay, and this presence of this field in the vacuum is called the amount of this is called the vacuum expectation value of that field that we have. So that is not zero in the Higgs mechanism for the scalar field. And as I said earlier, we don't want this field which is present in the vacuum to be detected otherwise. Okay, we can detect this only through interaction. There, it's interaction with the elementary particles through their masses. Okay, so the mass of these particles is the only indication that we have these fields in the vacuum. Well, that is not exactly so. There are other aspects to that in terms of the interactions of these particles as well. But mass is one of the things that it will show up, and there is no other way of showing in the terms of, say, for example, electromagnetic interactions or gravitational interactions, which is also not entirely true in a sense. Well, in the day-to-day or in the laboratory or terrestrial experiments that we consider, the vacuum energy or the presence of this in terms of in its interaction with, or the presence of that in the gravitational interaction, etc., is not detectable. But in the context of cosmological scales, that may have some statements to make. So the vacuum, the total energy or the energy of the vacuum will be important there. Okay, that we will not discuss today. We may discuss in the next live session, perhaps. I will at least, along with other things, I will indicate that as well there. Okay, so for the time being, we cannot actually look at, I mean, understand this. Therefore, this field that we have in the vacuum should not have an electric field. So these particles are therefore taken as a neutral, electrically neutral particle fields, and they also don't. They are also scalar particles. We cannot actually have spin for this non-zero spin for these particles. Otherwise, that will actually be detectable when we do certain transformations. Say, for example, any of the generalized Lorentz transformation, we would be able to detect these things. But that, I mean, it will have different implications. So that way, we need it to be a scalar particle and neutral particle, electrically neutral. Not only electric, yeah, it is electrically neutral, and it is yeah. So that is the way that we see as understanding the generating the mass for this photon here. Photon in the sense that we don't want the photon to be massive. I mean, so the standard model has taken care of that part, but the toy model that we have considered here will be actually generalized to the actual electroweak interaction, which includes the weak interaction and electromagnetic interaction. And there we will see that this particular way of doing things, we will have the W and Z bosons acquiring mass through their interactions with these scalar fields. Okay, so yeah, so this is what I was telling you. Okay, this is the details are worked out here. I think I will share the slide somewhere. Oh, I think last one also I said so, but somehow anyway, you will see this. You can see this video anytime, I guess. Or slides I can actually upload somewhere in the course website. Okay. So essentially, the mass of the W boson is denoted here as W, and the mass of the Z boson is denoted here as Z. This can be, and then in a very cute way, in the standard model, the mass of the photon comes out to be zero as required. In fact, it's not entirely an accident or something. Like, it's basically because of the design, the way that Higgs mechanism is designed, that the photon is massless. Okay. Well, the technical details are slightly more complex to explain here. At some later time, in a more advanced course, you will learn that. Okay, and similarly, there's this the fermionic mass can also be generated through the interactions of this. We will not go into the details of this, but just for the curious minds, I will spell out some of the names and some of the terminology. This is called the Yukawa interaction of the fermionic particle, which is basically an interaction with the scalar particle that will give the mass for the fermionic particle. And that's the way that we understand the electron mass as generated, or any quark mass is generated in the standard model. You can see that it is the same Higgs field, a single field, which is giving mass to various different things, and then it is also there in the interactions of this. There as a scalar Higgs boson each other. All of these are dictated by certain coefficients, certain couplings, and the value of the Higgs field in the vacuum. Okay, and therefore it has to be self-consistent. Experimentally, we can detect. Experimentally, I mean, independently, we should be able to measure them or find out what is the mass of the electron or other particles, and similarly the gauge bosons, etc. So these interrelations are very important. For example, there is a parameter called rho parameter in the standard model. The value of that is equal to 1, and experimentally you can actually find out this independent of the theoretical measurements, and it is exactly 1, excepting for some small deviation at a 10 power minus 4 or 5 level. Okay, 10 power minus 4. For the time being. I mean, this is slightly old, but I don't think the numbers have changed quite a bit. Okay, and how exactly did we discover the Higgs boson, and then what are the ways that we detect an elementary particle, and then measurements are done at the, for example, Large Hadron Collider, etc. We will discuss in the next live session. Okay, I think I will kind of stop here and then see if there are any questions. So since I don't see any questions as such, um, so we can stop here and enjoy the rest of the course, and then have a nice day.